All right, about to begin. Just got to get rid of all that text. Okay, so continuing with calculus, we'll be talking about the squeeze theorem today, and a couple other theorems as well. So, like before, we're following the Stewart book, single variable calculus. Possibly we'll get into some multivariable in a week or two or more. Right, so let me just write down the title. And last time we just introduced differential calculus. We talked about functions. We didn't define sets or anything, but we said, functions were a particular type of relations between sets. And then we talked about limits really briefly. We wrote down the definition and a couple of the properties, I believe. So yeah, so this will be lesson 7. We're going to continue. We're going to talk about the squeeze theorem. This is one of the first theorems that you're introduced to in calculus. So squeeze theorem, and we'll say and others. Okay, and the squeeze theorem is it's a theorem about limits, so it allows you to sort of use other functions that are related to a particular function that you want to find the limit of. And the general picture is, well, let me draw the picture first before writing the actual theorem, because I think the picture kind of just says it all. You have a function h. It takes on some values. So yeah, let's say we have the real number line here, xy axis. Oops, totally messed that up. I'm not sure how we want to do that, but the x is the usual horizontal axis. You have your y-axis. So let's say there's some function here h, and let's say there's another function f. And when we get really close to some point, let's say like right around here, they approach the same limit at this point right here. And let's say in addition to these two functions, f and h, there's also a function that's sort of wedged in between them. So it doesn't necessarily have to be true for the entire domain of the function, but at least near that point, you want the property that the function in the middle is squeezed between the two. So like there's some, I'll put it, or maybe I should write it with a different color. So you have your blue functions here, and there's some black function in the middle that's wedged between them. So here's your general picture, and the black function is g. So you have h of x is less than or equal to g of x, which is less than or equal to h of x. And this needs to be true not necessarily for every x, but every x near some particular point where you're trying to evaluate the limit. And the function that we're trying to find the limit of is the one in the middle, the squeezed function, the g of x, that's in the middle of h. Oops, I wrote h twice. H and f. So f is your small function, h is your large function, and the limit of f and h as you get close to some point is equal to each other. And the theorem says, well, then we know the limit of the function that's squeezed in the middle, it has the same limit. Right. So let's write down the theorem, but that was basically the that was the idea, right? So we have two blue functions, h and f. They have a particular limit at a point, and it's the same value. So this is some limit L. And then you have some function g that's always between them. It has this property that it's always greater than f, but less than h. And if it has that property for all values close to that limit point, and we know that the limit of f and h exists, then the theorem says that the squeezed function in the middle has the same exact limit. So we'll write that more formally right now. Okay, so basically you have, like we had before, we have these three functions, f, g, and h. And it says, so they use kind of vague language in the book. They say when x is near a. But in more mathy type of language, right? In topology, we would say there's some open set that contains a, and whenever x has any value within that open set, then this is true. But they just use kind of loose language here. They just say, okay, well, we need f of x to be less than g of x and less than h of x when x is near a. So they're kind of being a little vague here, but there is a way to make this more precise in topology. And they also point out that it doesn't have to actually be true at a. So whatever the value, the functions actually don't even need to be defined at a. They could just have limits. And in fact, I believe that example will show up frequently when you have like some sort of sine of 1 over x or something, and you're looking for the limit at 0. The function like in the middle might not even have a value. And they say except, so they say except possibly at x equals a. Right, so we actually don't need this inequality to hold at x equals a, just for all the points that are near x equals a. So if this is true and these functions on the outside have limits and it's the same limit L and it exists, then the theorem says that the function in the middle has the same limit. So if this is true for all points near a and the limit as x goes to a of f of x is equal to the limit as x goes to a of h, and we'll just call this L. Then the theorem says, well, then the squeezed function, I like to call it the squeezed function. I don't know if that's the common terminology, but g of x is the function that's squeezed in the middle. That function, the squeezed function, has the same limit L. So if the outside functions have a limit and it's L, they're both equal to L. It's very important that they're both equal to L. Then the limit for g exists, and it's also L. And I'll just say also here to put some emphasis on this, right? So this is kind of the what we need to be true for the theorem to hold, right? We need f of x to be less than g of x to be less than h of x for all points near a. We don't need it at a. That point doesn't really matter. And we need the two outside functions to have the same limit L. Then the theorem says that, okay, well then the function, the squeezed function in the middle, that also has limit L. And that's basically the theorem. And you might be asking, okay, well, this is like a lot of, like what do I use this for, right? So a lot of the times what you're going to use this for is you're going to know the value of the limit for the outside functions, and you're going to have some sort of complicated function in the middle, possibly that you're just struggling. You don't have normal limit laws to figure out what the limit is. Like it's not a polynomial. Maybe it's not the composition of like an absolute value in a polynomial or an absolute value in a square root, or some sort of combination of compositions of continuous functions that we know how to deal with. A lot of the times the function in the middle will have like, product with some sort of cosine where it's like cosine of 1 over x. It's very hard to deal with directly, but you can always bound cosine by like 1 and -1, and then so a lot of the problems will involve bounding sine and cosine, or finding estimates that, just a lot of the problems basically center around trying to figure out what is the h, what is the f, and usually you're given the g and you want to know what is the limit, right? So yeah, that's how a lot of these problems work, right? You're just looking for, you're trying to find the limit of some squeezed function. You try to find what can I squeeze it between, that I know the limit of already. Okay, and then last time I was about to do number 27. I think this is page. Where is this? I think it's 2.3. Yeah. Page 111 in the Stewart book. Number 27 was a squeeze theorem problem. And I mentioned it last time, but I said we would kind of skip it, so now I'm going to go over it. Hopefully this board does not fall off the wall while I'm doing this. Oh, there we go. All right, so page, what did I say? This is section 2.3, page 111, number 27. Just write it like that. And this is a squeeze theorem problem. Right, so it says use the squeeze theorem. Basically, we want to find this limit. So x goes to 0. Oh, wait, no. Different problem. X goes to 0, and it's x squared cosine of 20 pi x. Right, we want to show that this limit is 0. Right, and they kind of give you the functions in the problem, so this one's not very difficult. It's kind of seems like a more introductory problem. They tell you that you can squeeze this between two functions, f of x, which is negative x squared, and h of x, which is positive x squared. And the reason, like I was saying before, the reason you can do this is because cosine of anything, no matter what, they love to trick you by plugging in something complicated in here, but you always have to remember that cosine of anything, no matter what you plug in here, is always between -1 and 1. And so that allows you to say that we know that this function, the smallest it could possibly be, would be if cosine of whatever this was -1 exactly. And then this would just be negative x squared. And, you know, the largest it could possibly, this factor could contribute is, well, it could be 1, and then we would just get x squared. So that's, you know, that's sort of your intuition for why this should work. And now we know that this, these two functions squeeze this function. So if we want to know what this limit is, we can squeeze it between these two functions. These two are just polynomials. They have limits. They're continuous functions. So we can just plug in the value. The limit at 0 is just 0. Right, so since these both have limits equal to 0, and because they strictly bound this function, meaning that like x squared is always greater than or equal to this function, and negative x squared is always less than or equal to this, and because they have the same limit, which is 0, then that tells us that this limit is also 0. And that's basically how you look at these problems. And then it says like use a graphing calculator. I'm not going to use a graphing calculator, but let's just draw really quickly like what is this going to look like, right? Well, this cosine's basically just making it oscillate very frequently, basically like 20 times more frequent than normal, right? And it's going to be bound between x squared and negative x squared. So if we draw x squared, negative x squared, something like that, then this function is just going to be like oscillating between these two very frequently, something like that. And so you can see that even though this function is acting wildly when we get away from 0, as we get closer to 0, it gets kind of squeezed between x squared and negative x squared. And since those functions have a value of 0 at 0, they sort of force the limit, even though it was acting wild outside. Once it gets close to 0, it sort of gets squeezed and has to have the same limit. So has the limit of 0. So that's 27, and then 28 is a similar type of squeeze theorem problem. So let's do that one as well. All right, so problem 28. So it says use the squeeze theorem. Essentially, it says use the squeeze theorem to show that this particular limit is 0. And it's x, oops, a little messy. So x cubed plus x squared. And that times the sine of pi over x. So now instead of sine or cosine of something times x, now it's sine of pi over x. It's a little bit more complicated of a function. In particular, it's not defined at 0. So that's, we don't need our function to be defined at 0, but if we had a continuous function and it was defined at 0, then we know the limit is just the value of the function. Here, the function's, it's definitely not continuous at 0, it's not even defined at 0, right? So we can't say it's continuous at 0, but we want to show that the limit is 0. And even though this sine of pi over x is not defined at 0, we can still bound whatever sine of this is, even if it's a really large number, right? Remember, no matter what sine of this is, it's always between 1 and -1. So here, we're going to say that this function, let me call this, what did we say the one in the middle was, like h, I think? G is the one in the middle, so let's just call this function g. And so we know that g is always less than or equal to square root of x cubed plus x squared, and is always greater than or equal to negative square root x cubed plus x squared. And again, we have even though the function's not defined at 0, we can still bound sine of whatever this is. So like I said, it's almost better to just forget what's in the sign. Just say, you see a sine of something, you see it's a squeeze theorem problem, you know you're probably going to have to bound it between -1 and 1. So at its most, sine of whatever this is 1. So this whole thing is at most x square root of x cubed plus x squared. Likewise, you have -1 is the smallest it could be. Again, you have a similar type of situation where now we have a composition of a square root and a polynomial, which are two continuous functions. They're both defined at 0. I can just plug in 0 here. I should get the limit, which is 0. So this has limit 0. This has limit 0 as well. -0 is 0. And that forces the limit in the middle to also be 0. So then that tells us that this limit is 0 by the squeeze theorem. And if we didn't have the squeeze theorem and we tried to prove this from the definition of limit, with no theorems or anything, no limit laws, no nothing, that would be very difficult. But of course, in mathematicians, they love making things easier, right? So if it's hard to do something brute force, or we like to come up with theorems that make these problems easier. So this is kind of like one of those theorems where if you pick the functions nicely, then the proof is very simple. It's always squeezed between these. These are continuous. They have limits. It's 0. They're both have limits equal to 0. Therefore, the function in the middle is also has a limit equal to 0 as well. Okay. So that's the idea of these squeeze theorem problems. Of course, I can do many, many more of these, right? But I don't want to waste time with a 2-hour-long video where I'm just doing squeeze theorem problems. If you want me to do more problems, of course, you can contact the email, mathpondofficial@gmail. But yeah, some of these get a little more complicated. Sometimes you have to put estimates on parts of the function to be able to bound it one way or the other. So they can get a little bit more complicated, but this is the general idea, and you'll see the sine and cosine show up a lot in these types of problems. Okay, and then I sort of said this really quickly last time. Drop my marker. But we said that a function was continuous if, here I'm going to be a little bit more explicit. So definition, a function f is continuous if the limit as x goes to a of f of x is equal to f of a. And what I mean by explicit is here we're really saying three things, and this is kind of glossed over a lot, so it's important to point this out when you're learning this for the first time. This statement here is really saying multiple things. So one, it's saying that f is defined at a, x equals a. Not only is it defined, but the limit as this limit exists. That's the second thing. And so not only is the function defined at x equals a and the limit as x goes to a exists, but the third thing is that it's actually equal to the value of the function at the point. So the limit is actually equal to f of a. And it's possible for the function to be defined there, the limit to exist, but it not be equal to the function. For instance, you could have like a removable discontinuity where the function jumps at the point, or a jump. Sorry, it's not remove. It's a jump discontinuity, right? If you have a jump discontinuity, then 1 and 2 would be satisfied, but the limit would not be equal to the value of the function because the function jumps at that point, and you get a different value than the function is defined to be a different value than what the value is approaching as you get close to that particular x value. Okay, so you have these three things here. It's continuous if it's defined there, the limit exists, and the value of the limit, that L that we had in the definition, is actually just equal to f of a, the value of the function. Okay. And then I'm going to write down a few additional theorems. So these are all very important theorems when you're finding limits, taking derivatives. Later, I guess we'll be kind of writing down the from definition, solving derivatives using limits, and so we'll need a lot of these theorems. It involves, like, when you have continuous functions, you can add them. It stays continuous. If you multiply continuous functions, they're also continuous. You can divide continuous functions, like when we took polynomials and we divided them, then rational functions were also continuous as long as the denominator was not 0, because you can't divide by 0, of course. So let's write down a few of these theorems. First theorem just involves those compositions, sums, and products, like I just said. And let me try to fit this all on one board so I don't have to keep erasing. Or maybe I'll do two at a time, or let's see. So yeah, first theorem says that if f and g are continuous at a, and c is a real number. So again, I'll use this set notation every once in a while, but don't get fooled by it. There's very few notation you really have to know for math. It just says c is in the set of real numbers. So c is a constant. Then the following are continuous. Probably not going to fit this all here, but so you can take f plus g, or f of x plus g of x. This defines a new function. That function is continuous at x equals a. You have f minus g, of course. Take the difference of the two, that's also continuous. You can multiply your real number constant by the function, and that stays continuous. So you can just scale the function up or down. Still continuous. The fourth thing you can do is you can multiply the two functions. And as long as they're both continuous in A, then the product, there's no problem. The product is also continuous. And you can divide the functions, f divided by g. And as long as the bottom function is not equal to 0 at x equals A, then the limit will exist, and the limit is just the, it will be continuous at x equals A. There's also, there's limit laws. These are very similar to the limit laws from one of the previous sections. I didn't really go over them because, I didn't want to go over this twice, basically. But these are very similar to the limit laws, and you're basically proving them the same way. Like, f and g both have limits. At x equals A, it's equal to the value of the functions. Therefore, I know that it's continuous because the limit is equal to the sum using the limit laws. The limit over here is equal to the product using the limit laws. Same thing with all these others. So essentially, I didn't want to write out everything twice, but these are sort of equivalent or derived from, you could say, the limit laws in one of the previous sections, where like if you have two limits and you add the two functions, that also has a limit and it's equal to the sum. Same difference, scalar multiplication, products, and division. Okay, so this is the first theorem. I was trying to write it a little bit smaller, but unfortunately I took up the whole board. So yeah, these are very similar to the limit laws, but now we have a statement for continuous functions. The sum of continuous functions is continuous, and etc. I don't want to repeat myself. Okay, and then the second important theorem from this section. Let's see. So if f is continuous at B, basically it's a theorem about composition of functions and continuousness, I guess you could say. So if f is continuous at B, I guess I mean at x equals B, and the limit of g is equal to B, at A, as the limit as x goes to A, then the statement is that the limit of the composition is just equal to f of B. So you have f is continuous at x equals B. As you plug in values really close to A, g of x is approaching B. And therefore, if I take the composition f of g of x, well, the thing I'm plugging into f, g, is getting really close to B, and f is continuous at B. So this theorem just says, well, the thing that you think is going to happen basically happens. G gets really close to B, and this limit gets really close to f of B, because f is continuous. Oh, excuse me. Need some water. Okay. Sorry. So yeah, just one more time. So f is continuous, so when I plug in values really close to some x value, I should be getting really close to f of that value. And it says that if I plug in values close to A, g is approaching B. And therefore, in the composition, if I plug in values really close to A, this should be getting close to f of B. And this is only true because f is continuous, and you're allowed to kind of just plug in the value of the function in some sense. You can think of it like that. This thing on the inside is approaching B, f is continuous, therefore I can sort of just plug that value into f and everything works out nicely. But this is not necessarily true unless f is continuous. So you really need f to be continuous to have this. Okay. I'm going to go through these just a little bit quickly. I don't want to say they're easy. They're not like easy theorems, but they're kind of basic in the sense that you build more complicated stuff off of them. This is just a statement saying like if the outside function is continuous, right? You want to just be able to plug in f of b, right? That makes computations very easy. But of course, if f is not continuous, then you can't do that. So this is just saying, as long as f is continuous, then you're good. You can just plug in b into f, and then you get your answer. Oh. Throat's a little sore. Okay, third theorem. So we'll call this like three out of the 4 little theorems. Well, actually, the last one's a little bit bigger. So we'll say this is like 3 out of 3 of the small theorems. So if G is continuous, at A, and F is continuous at B, or no, sorry, at G of A, which I guess you could call B, but we'll just call it G of A. Then the composition is also continuous at A. Which one's that? So F of G. Okay, so you have your inside function G is continuous at A, and if F is continuous at the value of G at A, then you can compose the two, and it's continuous at A, and of course the limit as x goes to A is then just F of G of A. Okay, so a couple theorems about continuous functions, compositions of functions, right? And then we said all the different ways we can combine continuous functions to get new continuous functions. We can add them together, we can subtract them, we can multiply them together. What am I missing? We can divide them. As long as the function on the bottom is not equal to 0, then it's continuous. And yeah, and then we had a couple of theorems about compositions. Okay, and then now the last theorem I wanted to talk about before we go into another exercise, calculus exercise, is the intermediate value theorem. This is a very fundamental theorem for calculus. It's not the fundamental theorem of calculus, but it is one of the most important ones, I would say. And you kind of, each one of these, I'll call them like the more basic main theorems, they're sort of all building up to proving the fundamental theorem of calculus. So you can kind of think of this as like a pre-fundamental theorem. This is like the stuff that you're going to prove in order to prove the fundamental theorem. And this might all just be gibberish, because if you've never seen the fundamental theorem of calculus, then you don't know what I'm talking about right now. But yeah, just consider this one of the main ideas of calculus. It's one of the main theorems, but not the fundamental theorem. So it's called the intermediate value theorem. or the IVT I've seen a lot, intermediate value theorem. And this is just a really nice theorem about real numbers, and the idea is that if you have a function f here, and let's say it's defined at f of a to have some level here, there's some higher level here, f of b. What I mean by level is that just the value of the function at these 2 points is these 2 values, and we don't know what the function does in between. Let's say, this is some interval a to b for the x values that we're plugging in. So we don't know how we get from this point to the other point, but the theorem says if we know that the function f is continuous, meaning that I didn't lift up the pen when I drew the line, and we know it goes from here at a to a f of a to b f of b, then the theorem says that it hits every point in the middle, that there's some sort of property of the real numbers that there's no holes missing, that if it's a continuous function and I'm traveling up from f of a to f of b here, I basically have to hit every value in between. So there's really no values I miss. If I pick any value in between f of a and f of b, somewhere here, like n, some intermediate level, then there's at least one value in this interval a to b where the value of the function is actually equal to n. In this case, I think the way I drew it, there's 3 here. But the theorem just guarantees that there's at least one value. So here, this would be c1, c2, and c3. These are 3 different x values that f of those values is equal to n. And the intermediate value theorem says that if you have a continuous function, it's necessarily true there has to exist at least one of these c's. There could be more than one. In this case, there was 3, but the theorem says there has to be at least one. So I'll write that formally. But yeah, you have this interval. You have to be a little bit careful about, the function has to be defined on this whole interval. If it's not defined on the whole interval, then it could actually jump up and miss values. So you do have to be careful about the hypotheses of the intermediate value theorem, but assuming the function is defined on this entire interval, it's taking one value on one end and another value on the other end, and you know that the function is continuous, then you get the theorem. So you have to be a little careful, but not too much, usually. So this is still the intermediate value theorem, right? Intermediate value theorem says that suppose f is continuous, on a closed interval, a to b. The brackets here just mean that I'm including the points, so it's every point between a and b, including the endpoints a and b. So suppose f is continuous on every one of these points. It's closed interval. And let n be any number in the interval. But we're not going to pick the endpoints, or sorry, actually, no. I want not a and b. So we want to say let n be between f of a and f of b. Assuming, of course, that f was larger at b than at a. If it was the other way around, we would just write the inequality the other way. But the main point here is that if you pick a number that's between f of a and f of b, then we can always find some number on the inside of this a-b interval such that when I plug in that value c, I get exactly n, no matter which n I pick here. So it's very cool that I can pick any n. And that's really just a property of real numbers, the fact that there's no holes, there's no points missing. I can actually pick any n in between here. Then there exists a c inside a to b such that f of c is actually just equal to n. Exactly. So it's not close to n. It's not like, you know, it gets closer and closer to n as I get closer and closer to c. No, this is exactly equal to n. There's some real number c that's between a and b, so it's somewhere in this interval where the value of f at that point is exactly equal to n. No ifs, ands, or buts. And it just says one of these points has to exist. It doesn't tell you how to find them, which is actually a big problem in finding the roots of polynomials. Like, this theorem will guarantee that the polynomial has roots, but it doesn't give you any sort of procedural way to calculate the digits of that number, for instance. In order to do that, you need maybe like Newton's, is it Newton's method, or yeah. And there's iterative methods, you know, to try to find roots of polynomials, but you can use this theorem to prove that a polynomial has a particular root in an interval, but you can't actually necessarily figure out what that value c is. And a lot of the times, there will be no algebraic description for c. It'll just, you know, like I said, you'll need some sort of iterative calculation that will help you get more and more decimal places of the number, but you'll never be able to write it down as like a power series necessarily, or some, well, a power series you can, but that's what a decimal is. But you might not have any sort of like simpler algebraic way to express the value. Okay, so yeah, mainly used for polynomials, but theoretically you can use this for a lot more stuff. This is, I have to relook at the proof, but I think this is used in the mean value theorem somewhere, or I know you use the mean value theorem in the fundamental theorem, and I think you use the intermediate value theorem in the proof of the mean value theorem, but don't hold me to that. I guess I'll look that up again for one of the following lessons. But yeah, either way, very fundamental theorem. It tells you stuff about polynomials, roots of polynomials. It tells you, you know, usually a lot of the times we're trying to solve these equations, so this calculus gives you kind of like a nice way to get an existence proof, to say, oh, like this polynomial has a root, or, you know, this particular function takes, we know for sure there's some value where it takes that value on. Maybe we don't know how to calculate it, but we know it exists. So that's a lot of the times what it's used for. Okay, and then getting a little late here, so I'm probably just going to do one or two more problems from, I think it's 2.5, yeah, section 2.5. Oh, no, I wrote 2.5. Oh, yeah, 2.5? Oh, I wrote 2.5. I think I meant 2.4, yeah. Yeah, so page 123, I wrote 2.5, but I believe it's actually 2.4. Okay, so 2.4, page 123 in my book. I don't know, maybe it's something else in yours, but I think the sections should be pretty close. This is number 41. And it's exactly what I was just talking about. So it gives us a polynomial. Right here. And it wants us to show that there's some root of the polynomial in the interval from 1 to 2. So there's some number between 1 and 2, strictly between 1 and 2, where this, I can plug it into x and I get 0. So show, I'll write it in math, math notation. So there exists a c in the interval 1 to 2 such that, and we'll call this polynomial f of c. c is equal to 0 exactly. So we have our polynomial. We want to show that there exists a value from 1 to 2, at least one value, maybe more, such that when I plug it in, I get 0. And very simple, we look at the endpoints. We're going to use the intermediate value theorem. The value at one of the endpoints, if I plug in 1 here, I get -1, right? 1 plus 1 is 2 minus 3 is -1. And if I plug in 2, I get 2, 4, 8, 16 plus 2 is 18 minus 3 is 15. All right, so the value at one of the endpoints is -1. In particular, let's point out that it's negative. And then the value at the other endpoint is positive. Since 0 is a number between, and like I said, for finding roots, you're always going to find one endpoint where the value is negative, the other endpoint where it's positive, and since 0 is always between any negative and positive number, then we can use that as our n and say, okay, well, n equals 0. There must be some value by the intermediate value theorem in this interval where the function at that point is exactly equal to 0, and it's a root. So by the intermediate value theorem, that gives us basically our answer. There exists a c in this range, 1 to 2, and when we plug it in, we get exactly 0. All right, it's a little small down here, but basically I'm just saying exactly what we were showing here. I found a negative value on one interval. I found a positive value on another interval. I pick the theorem says if I pick any number between -1 and 15, there should be some value c in this interval where when I plug it in, I get that. So I say, okay, let n equal 0. Intermediate value theorem gives me the c, and we're done. But like I said, we don't necessarily know what the decimal expansion of this number is. We don't know. We don't know if it's the only value. There could be more than one value. Yeah. And we don't necessarily have any algebraic description of the number either, if it is unique. Or if there's multiple, we don't have an algebraic description of any of them necessarily. So it's more of an existence theorem if you want to show that some number necessarily has to exist and have that property, even if you don't care what the form of the number is or what the size of the number or the exact decimal expansion. So that was 41. Same page. I'm going to do 54. Or same section. I don't know if it's the same page. But yeah, same section. So 2.4, problem 54. And actually, I just want to do the last part of the problem. I think the other parts of the problem are interesting, but I think this is really the interesting problem. So it's a problem about functions and composing functions with the absolute value function. So here it says if the absolute value of f of x is a continuous function, does it follow that f is continuous? And we're asked to either prove that it's true, that it's always true, or we have to give a counterexample. And this is a common thing in math that if you want to disprove a particular theorem, sometimes it's enough to just offer one example where the theorem is not true, and therefore the theorem is not always true. So here, if f of x composed with the absolute value of f of x is a continuous function. We either want to prove, if it's a continuous function, then f of x is continuous. So it's actually, it's an if-then statement. If the absolute value of f of x is a continuous function, then f of x is continuous, and then we're asked either prove this or give a counterexample. And so I'm going to disprove it by giving counterexample. So this is not a true statement. This is false. And a counterexample, which if you stop the video right now, you could probably figure out a counterexample on your own. But one easy one is to just have a discontinuous function that's always equal to either -1 or 1. And then when you take the absolute value, it's a constant function, which is continuous, but the function itself was not continuous. So an easy counterexample, I came up with one that was really simple. It's just equal to -1 if x is negative, and it's equal to +1 if x is greater than or equal to 0. This is a jump function. It has a jump discontinuity at 0 because the left limit is equal to -1 and the right limit is equal to 1. And it's a counterexample because we know that the left limit and the right limit are not equal at a point, therefore this can't be a continuous function. But the absolute value of the function is just always equal to 1, no matter which x I plug in, and therefore it's a constant function. Constant is a polynomial. Polynomials are continuous. I mean, constants are like the easiest thing to prove that they're continuous. So the absolute value of this function is continuous, even though the function itself has a discontinuity at 0. And therefore that disproves this theorem because we had the first thing true with the implication not true. So the absolute value of f being continuous is not enough, does not necessarily imply that the function f is continuous itself. So this is false, and this is one counterexample. But of course, there, I think there's like uncountably many counterexamples here. You could just move the discontinuity around. You can make more discontinuities, right? Yeah. So there's a lot of counterexamples here. Okay, I don't see any comments in the chat, so either everybody already knows this or there's nobody in chat right now. One of the two. But yeah, I hope if you're watching later in YouTube or whatever, I hope you enjoyed the lesson, and I hope you show up on Friday for 4 p.m. I've been doing Tuesday, Friday, 4 p.m. I'm just going to keep going with that and see how many videos I can put out. All right. That's all I have for today. All right. Thank you for watching.